So now let's just define these things. That red curve I just showed there is this Python code here. Not very straight lines here. So it's function normal, which you will see in the code distribution for this class, and it's also actually built into the Python library, but I happen to use my own trivial one-line definition as a Python function. And if we go to Wikipedia, which we know to be the source is particularly accurate in areas like this and particularly reliable, it will tell you all about normal distributions. And here I cut and pasted the actual functional definition from Wikipedia. F of x is 1 over sigma square root of 2 pi times this exponential with x minus mu raised to the second power and a minus a half. And that was not meant to go forward there. I apologize. Next slide here just gives the code that produces that green histogram, and we can probably think about this in a little detail. Here we're generating our million results. As I told you, we had 1 million people or 1 million physics results. These million results are just numbers between 0 and 1. So how do we get 40,000 counters out of this? Well, we just divide the region between 0 and 1 into 40,000 parts, each of which is equal size. That's what this is done here. We take the number between 0 and 1, multiply by 40,000. That gives us a number between 0 and 40,000, or 40,000 minus a little bit, because we'll never get the value 1. And then we make it into an integer, which runs between 0 and 39999. And then we increment, that's the place or the result or the answer or the physics final state over the 40,000 possible final states. And we increment the counter corresponding to this place. And so this counter here is the thing that gets histogrammed. And we initialize here in Python, we define an array of length 40,000 and initialize it to 0. We have the value, the xy text is the value in points of how much we're displaced from the point for the text, and then we have the actual xy value we're pointing at here. So this produces some text at this position here given by xy text with an arrow pointing to this position here given by xy. So here are 4 annotate commands, which is just useful. You will find that if you try doing these things, you spend longer on doing plots than you do doing arithmetic. So we've so far studied what happens when you have a mean of 25, and with the error, which is almost exactly, but not quite precisely, the square root of 25, then 5. But as we saw from looking at the details of the distribution, it is not exactly Gaussian. It's too small on the low side and too big on the high side. And so the theorem that the distribution is exactly Gaussian is a so-called asymptotic theorem. It only implies when the number of observation n is large, and 25 is big enough for it to be roughly right, but not big enough for it to be precisely right. So we'll go up to a factor of 10 to 250 as the mean, exactly the same idea, but just multiplying the average value per bin to 250 and multiply it by a factor of 10. This should give us more reliable answers. So here's a similar result, but instead of having 1 million people or 1 million physics events, we have 10 million. And we only have 40,000 possible answers. So now we have 250 as the midpoint. And here's the same normal distribution is now plotted with a mean of 250 and an error which is the square root of 250. And we've also plotted this 1% value and 99%. 99% of the events lie below this value here, and 1% lie below this value here. So, and here is 1 sigma from the mean, and here's 1 sigma above the mean. So actually, this particular green curve fits better the red curve than previous case, and we can see that later when we actually plot the error bars. And so this slide here goes through this what I just said. We have 10 million events, but still 40,000 categories. Square root of 250 is around 16, a little less than 16. We run the 1 sigma line from 250 minus the square root of 250 to 250 plus the square root of 250. We'll see later that the plots get rougher when we reduce the number of events, but we want to do a few other things before we discuss that. So we actually just want to show these error bars to show that the fluctuations are reasonable. These are just the square root of the the number of events in each of the bins, and you can see that the red curve with its error bars is quite consistent with the green curve, essentially wherever it's plotted. Here's this in a little more detail, and showing perhaps even too good agreement between the green curve and the red curve. And this is for this central region between mean minus 1 sigma and mean plus 1 sigma. Here's the same thing for here's the 1 sigma on the top side, and here it just shows even above there. It's still possibly there's a slight tendency for the green to be above the red, but it's not by very much. It was a much bigger effect when we had 25, and that's because 250 is a bigger number than 25. The asymptotic approximations that give you the Gaussian distribution are better. This just describes how I produce those error bars using matplotlib and the matplotlib command error bar. We already shown how we got the red curve, which is y25, was the normal distribution times the at the bin centers, and here are the error bars, errors, which is just the square root because y's are events, and we get the error bar by plotting it at the center. The ordinate, which is the x-axis, is given by the centers of the bins. The y value center is given by the normal distribution, and the error is just the square root of y25. And here we have the other things we want to do. We have a marker, which is an O, the color, which is a black, the size of the marker, which is 5, and I've scribbled over it, but there's also a line width specified in points. And we've already essentially seen this. This tells us how to make the 1 sigma line on these graphs, and it uses the plot command from just vectors of length 2, so this line is just a single line. If you do a plot like you do of the normal distribution, then you have longer vectors and you get a smooth curve. Yes, we're just doing one line.